I'm Alan Calder. I'm in the Department of Physics and Astronomy, and I'm part of the Nuclear Astrophysics group that includes Mike Zingale, Jim Latimer, Doug Swesty, and we have a couple of people here, Chris DeGrindle and Lupe Barrio Sazo, if I'm saying that right. And it didn't just change, right? Okay. I'm trying to embarrass Lupe. Anyway, I thought I would just give an example of the type of thing that the computing enables. And so the story is that we have a laboratory to play with blowing up stars, to then understand how they work, to then pin down the uncertainty in things that we see, mainly the amount of light that comes out of it, and then use that to learn more about the whole universe. So I'm talking about things that go from the smaller scales, things that I can't resolve in my code where we have subgrid scale models, to things that go all the way to the cosmology scale. And so I'm getting a little carried away. This is a galaxy, and I forgot to look up its name. Lupe, do you know this one? It was Supernovae 1994D, and it's got a name like NGC 4529, which is a line in the new general catalog. But the point is, a long time ago, and I love saying this, in a distant galaxy far, far away, a star blew up, and it was bright enough to rival the luminosity of all the stars in the galaxy combined. Not exceed it, but rival it. If you saw this at a distance, you might think there were two bright things that look similar. Well, we use these things as what we call standard candles. A point source obeys an inverse square law that if you double the distance, then you see a fourth of the light. It falls on 4 times the surface area for a given angle. And with these stars, assuming that they are standard candles, we can then measure distances. If you know how bright the standard candle is, then how bright it looks allows you to calculate the distance. So by doing that, and this is old news, but it's still profound, in 1998, we realized that if these are schematics of the evolution of the universe, you've got the past, the present, the future, time flows this way. We used to wonder if, well, there was a big bang, is gravity going to pull things into a big crunch? Or there was a big bang, are things just going to go out and stop? Or are they just going to go out and keep going? But what we learned via these standard candles, i.e. the thermonuclear supernovae, is that the expansion history is different than we thought. And the expansion is accelerating. And that tells us that something like 70% of the universe is this mysterious dark energy that we don't understand. And I put in this little area here everything we know about dark energy. So that's profound. I mean, that's as big of a change in our understanding of cosmology as going from the geocentric picture to the heliocentric, and then to the whole concept that we're not the center of the universe. 70% of the universe is something we never heard of roughly 20 years ago. So I work on modeling these things, and this is one way to blow them up. This is the interior of a compact star known as a white dwarf, and there's a little match head that I've ignited here. And this contour marks a density where the burning is going to transition. And now I got to figure out how to play movies on this. Let's see, here we go. Oh. Well, this is what it's supposed to be. Oh, crud. Well, should I switch to my laptop or should I just act it out?
Take directly from the folder instead of from PDF. Oh, wait. Yeah, just here, if you scroll.
Yeah. Let's see if that'll do it. Yep. Okay, so this is a fail.
Go to the Finder. Have to click on the file directly.
Well, I can't make this go away, so lower left corner. I'm not a Mac guy. I'm a Linux guy. This is beyond my skill set. Sorry. Okay.
And here, which of these
That
two
one,
is?
that one, that one. So is it possible to just switch to, well, okay, so I will act it out. What happens is the match head grows and the flame gets perturbed with something called the Rayleigh-Taylor Instability. Okay, and give it up. It's hopeless. It's okay. You got to learn when to just declare a loss. So this instability grows, and these things become more unstable. And at a certain density, it transitions to a detonation that just blows up the whole star. And what you can imagine seeing is that the whole thing is expanding because you've got this hot burned region in the interior, and the density decreases. Okay. So what is this Rayleigh-Taylor instability? Well, it occurs when there's a dense fluid on top of a light fluid in an acceleration. It could be gravity or it could be impulsive. We call that the Rickmeyer-Meshkov case. But you've got the gravity going down, the density gradient going up, and where they cross, that's unstable. And this is something you can imagine. If I have a cup halfway full of water and flip it over, then things bubble up and spikes drop down. And I have a movie that's probably not going to play either, but this one's different, so we'll try it. Aha, that's working. So here's that Rayleigh-Taylor instability in effect. And you can imagine if this were a flame with a density contrast, as this surface area increases, the burning rate increases. And so this is going on the scales that I acted out and on the scales that you can't see. We have a subgrid scale model for this Rayleigh-Taylor instability. So it's a contest, and these are simulations that Mike Zingali ran some time ago. It's a contest between the flame burning out small-scale structure and the development of small-scale structure. And the idea of the transition to a detonation is that at some point, a bit of fuel gets wrapped. Here, the fuel is in red, and it cooks off, or there's a certain fractal dimension in the surface area or something like that. But the key is, it's a race between flame speed and fluid instability development, and as you decrease the density, the flame speed slows. Okay. So going back to my simulation that you can't see, this is a different variable. It's going to expand, detonate, and the amount of expansion determines the density of things when they burn, and that determines the composition, and that determines the brightness. And so by changing the flame speed, we change the transition density, we change how much expansion there is, and we change the composition because the stuff that only gets made at high densities, there's less of it because it's expanded and the density's dropped. And that's what I mean by a laboratory, where you've got centimeter scale nuclear burning inside of a star. And the upshot is, this is a series of simulations. This is the mass of iron group elements versus simulation time. The detonations happen here, where all we did was change the flame speed that allowed the star to expand a little bit more before the small scale structure in the subgrid scale model we think developed. And that non-linearly changes the yield of these iron group things, and that, via the decay of radioactive nickel-56, changes the brightness of the star. So in our models, the brightness depends on the details of the flame speed and that Rayleigh-Taylor instability, and that depends on the composition. So we can relate. This is metallicity in these funny astronomy units, which is the log of the ratio of iron to hydrogen compared to the solar ratio of iron to hydrogen. And this is that nickel-56 mass, the decay of which is responsible for the brightness. Our results are here in red. We see this decay. As you increase the metallicity, the flame speed increases, you get more expansion, you get less iron group stuff. The experimental results are in black. They're large error bars, but we agree with the general trend. So we've offered an explanation for why some stars in an old environment with many reprocessed elements appear dimmer, it's because the flame speeds are faster, the star expands more in this model before it blows up, and you get less of the heavy stuff that produces the light curve. And that gets us to questions and discussion.
Okay, I'm going to ask a question, because you said something that was a little bit shocking. Buried in the discussion of stars, which are presumably thousands or tens of thousands of kilometers big.
Yep.
You mentioned centimeters?
Yes, the nuclear burning, the flame is about as wide as my thumb, and the star is the size of the Earth. And so that's 10 or 12 orders of magnitude, and you have to have subgrid scale models. This touches a lot of physics. That Rayleigh-Taylor is an example of a fluid instability. The thing is convective, so there's background turbulence. And we have models to account for that in the burning, because, as I hope I got across, the result depends non-linearly on how that flame speed changes, because it burns a while and then detonates, which I was able to act out. I hope that got across.
Good. I'm glad the movie didn't work. That was good. Okay.